Hello everyone, welcome to today's webinar, The Best Practices for the Best Consumable Life in Performance, Part 2. I'm Michelle Avila and I am your moderator for today. I am here in New Hampshire with Jim Colt, today's presenter, and we have a lot to go through, even more than last week, believe it or not. I think Jim's presentation is quite long, so I'm not going to spend too much time talking at the beginning here. I can just give you a quick overview of Hypertherm, though, although if you heard last week, you probably know all about it. But founded in 1968, nearly 50 years ago. We're in New Hampshire. We are an associate-owned, fancy way of saying we are an employee-owned company. All of us own the company, and we devote a lot of engineering resources to cutting research and development and hold a number of patents, some of which you will hear about today. Our product line, in addition to plasma systems, the topic of today's webinar, we also have laser and water jet cutting systems, as well as our CNCs and torch height controls. Software, we have both 2D CAD/CAM nesting software and 3D robotic CAD/CAM software, as well as consumables for both Hypertherm and non-Hypertherm cutting systems. And with that, I will hand things over to Jim so we can get going.
Welcome, everybody. We're going to continue with what we started last week, which was talking about how to make your consumables and your plasma cutting system last as long as possible to get the most out of them. And as we could back up just a little bit on the electrode functions that we were talking about last week. What hopefully we learned last week was that sometimes using your consumables until they fail, until catastrophic failure, is actually detrimental. It actually can cause damage to the rest of the consumable parts in the torch and end up costing you a little bit more money. So we spent the whole presentation last week just talking about electrodes and how to kind of judge when an electrode's going to fail, because when an electrode fails, it can easily take out the nozzle and the shield. In reality, could even cause some torch damage. That's kind of rare, but it could happen. So electrodes are very important when it comes to that. So, well, let's get started. And today we're going to talk about the rest of the parts in the torch, the swirl ring, the nozzle, the shield, as well as the torch body itself. Won't be, I think there's a few more slides, but I think we'll buzz through them a little quicker. And just like last week, I want to warn a little bit, all the pictures in this are actually pictures of a Hypertherm high-definition class HPR XD system, which is a liquid-cooled 100% duty cycle torch like you would see in a big production facility cutting plate, designed to run 3 shifts a day, 365 days a year. It's a high-end system. However, all the wear patterns and things like that we're talking about apply to virtually every plasma cutting system that uses shield technology like a Hypertherm does. So you can kind of go with what we're talking, even if you're using an air plasma such as a PowerMax system. So we'll move on a little bit, and I'll back up one more thing. With today's long life oxygen cutting technology, plasma is the most productive, cost-effective way to cut carbon steel from gauge to 2-inch thickness. Of course, we can cut other materials as well, but about 95% of the users of our torches spend most of their time cutting steel. So to get the highest performance, operators need to ensure that the consumables in the torch are inspected and maintained to high standards, and that's what we're here talking about today. So the first part we did was about the electrode. I believe that's recorded, and is it posted on the website now?
Yes, it's recorded and up on our website at hypertherm.com.
And you find that by going to the Education tab?
Training and Education at the top, and then clicking Webinars.
Webinars, okay, yeah. Very good. So what we talked about last week, you can easily go back and cover anytime. And we did want to, a question kind of came up last week about, we have 2 different types of electrodes that are used on some of our liquid-cooled torches. The left one is a standard electrode, and we say that you need to change those electrodes, or you absolutely should change those electrodes when the pit depth reaches about 40 thousandths as compared to a brand new standard copper electrode. But we also have longer life electrodes. You pay a little bit more for them but get dramatically more life out of them. And with those types of electrodes where you see a silver tip on the end of the electrode, you can go to 80 thousandths, twice as much wear. And that's because the whole idea of the silver tip, and if you can imagine that the silver tip costs more to manufacture, costs a little bit more to buy, but if you figure out the math on how many more feet of cut you get out of it, it's definitely a bargain. It's a good deal. And that's because the heat transfer is better. We can allow the hafnium emitter to wear twice as much as it does on a standard electrode, and that's the real advantage to it. So I thought I'd cover this briefly. And remember the electrode wear gauge. We're actually looking. We've noticed. We found out kind of after the event or during the event last week. We were talking about this wear gauge that we have in our inventory system here at Hypertherm. And we kind of had the part numbers mixed up, and we promised to get back to everybody with the right one once we figure that out. And I apologize for that as well. So in this webinar today, we're going to cover the nozzle, the swirl ring, the shield, inner retaining cap, outer retaining cap, and the torch. Once again, they look a little bit different than the ones on your PowerMax system or maybe another Hypertherm system or even another brand plasma, but a lot of the functionality is similar. So we're going to talk about nozzles first, and the HPR nozzle is a very unique nozzle. We'll talk a little bit more about how it works. It's actually a two-piece design, and if you walk out on our production floor and see how these nozzles are actually made, you'll be surprised that we can sell it for the price that we do. A lot of people look at the price and say, well, that's expensive, but when you figure it's cutting 5 or 6 miles of steel or even more than that before it wears out, and do the math on cost per foot, it's actually pretty inexpensive, and with the manufacturing techniques, it's amazing that we can make them as cheap as we do. We've really improved our technology over the years. So the HPR plasma nozzle is a very complex design that has to deal with the physics of high temperature gas flows and lasts for a reasonable time under very high temperature conditions. The nozzle's primary function, if this is in any plasma torch, is to constrict a very high temperature plasma gas. By constricting it, we're actually squeezing the arc, which increases its energy density and increases its velocity, which makes for a narrower cut with a lot more energy doing the cutting, and provides excellent cut quality as well. Another function of the nozzle is that it becomes part of the electrical process that ionizes the plasma gas before the actual cutting starts. In these types of torches, we use a high frequency, high voltage discharge that ionizes the gas, usually oxygen in an HPR torch, ionizes the gas that makes it more conductive and starts the cutting process. So as plasma cutting goes, HPR nozzles are very unique due to a patented, vented two-piece design, and I like to say they're an engineering masterpiece that provides for high-definition class cut quality with extremely long life. Now, there are other high-definition plasma cutting systems of other brands out there in the market. They don't use the two-piece vented design nozzle like the Hypertherms do. That's what really separates these from other systems. So when you think about the temperature of the HPR plasma arc that exits through the orifice of this nozzle, you'll wonder how an approximately 25,000 degree plus Fahrenheit electrically energized arc could exit through a copper nozzle that melts at about 1,100 degrees Fahrenheit and still keep cutting for 4 or 5 miles. Actually, the nozzle that's pictured in the center here is one that we talked about. There was actually a set of consumables, an electrode and a nozzle, that already had a lot of mileage on them. And this is from that same set that we talked about last week. And I believe it has well over, I think, 1.3 or 1.4 miles of cutting on it at this point. Okay. So the nozzle design utilizes proprietary gas swirl techniques, which is done by another component, the swirl ring. We'll talk a little bit more about that later. And it produces a centrifugal effect that effectively creates a cool layer of unionized gas between the arc and the copper nozzle inner bore to increase its usable life. It uses a double constriction two-piece design. We'll see it in one of the next pictures here. We'll point it out. That releases some gas pressure. It actually squeezes the arc once, then relieves some gas pressure back to atmosphere, and increases the energy density again up to about 4 times that of a conventional plasma. So if you've got a PowerMax air plasma system from Hypertherm, you might have about 12,000 amps per square inch energy density with those systems. If you also have an HPR XD high definition class plasma, you've got about somewhere between 12,000 and 15,000, between 45,000 and 60,000 amps per square inch. So it's generally at least 4 times the energy density of a conventional air plasma cutting system. So most of these features were invented and patented at Hypertherm a number of years ago when we first came out with our high definition class plasma. So just looking at the graphic on the right here, I'm going to use the pointer on the computer here and just point out a couple things. This is the inner nozzle, It's actually press fit into the outer part of the nozzle, and that's because we need a chamber in between the two nozzles. Where I'm pointing right now with a pointer is the primary orifice. So the arc actually is established in this area, and it gets squeezed by this first primary orifice, and then we relieve some pressure back to atmosphere. And if you look over here in the left graphic, you can barely see it, but there's a little tiny hole in the back in this area on the nozzle, and that hole allows the gas to release back to atmosphere. If you ever walk by one of our HPR plasma torches while it's cutting, especially with oxygen, you might smell a smell of ozone, which is that smell you get when you walk outside after a thunderstorm in the summertime, and that's what's actually venting out the back of this nozzle. Perfectly harmless. It actually adds a little bit of oxygen to the air, so it doesn't hurt you at all. And then once you get past that primary orifice on the inside, the secondary orifice where the arc actually goes out into atmosphere and does the cutting right in this area right here. You notice that the orifice is much smaller than the first one, so that's the second squeeze that gets the arc energy density up to 60,000 amps per square inch. So the critical features of one of these nozzles is the floating alignment between the nozzle, swirl ring, and electrode, and we'll see that in the subsequent slide, the way the parts all fit together. That assures accurate concentricity, which gives you better cut edge, angularity, and squareness. You see that with virtually all plasma torches need some way to align the electrode to the nozzle, to the swirl ring, and to the gas flow. It's kind of unique the way it's done with this one. The vented design offers the high-definition cut quality throughout the power range without sacrificing life as many other systems do. So superior cooling features, the high-definition class consumables, and especially the nozzle inside the torch, actually gets cooling water right down near the exit orifice of the nozzle, which is the hottest point of the nozzle. And another thing that's important with all of these consumables is that they're clearly marked with a part number and a batch code, which you can see in the left graphic here. Part number, the actual part number of the part. Compare that with your manual so that you make sure you're using the right nozzle for the right process. It does say Hypertherm below it, and there's a manufacturing batch code as well. The vent orifice up in this area on the right side picture that you can see here. So that's what the nozzle that we're talking about looks like. So I already did kind of point out most of these things: the primary orifice, the main orifice heat exchanger with water comes in contact with that area. Generally, if you see water dripping out the front of your torch, there's something misshaped on the front of it, and it allows a little bit of water to leak, and that's a good indicator that it's time to change the nozzle as well. So critical features. So this is actually showing the HPR nozzle stacked up. It's kind of hard to tell because all these pieces have a cutaway on them, so you can kind of see them. But this is the inner nozzle, right where the arrow is pointing at this point, and the electrode is on the inside of the nozzle. This is the cooling tube for the water cooling that comes into the system. The swirl ring, which kind of acts as the insulator, electrical insulator, and the alignment device. I knew I was going to do that with my arrow. And then you can kind of see the way the pieces fit up on the backside. So consumable parts alignment is critical to achieve in any plasma torch consistent cut quality. HPR consumables are manufactured to strict tolerances following CTF, which is critical to function quality monitoring procedures. In fact, some of the critical to function parts components on almost every one of the nozzles made for high definition plasma goes through a full inspection before it gets packaged up. So it's not just batch inspections where we inspect every 100th nozzle, but some of the dimensions are inspected on every single nozzle that goes out, because there are some critical dimensions on it. So only part numbers designed to work together, as suggested in the operator's manual, will produce the best results. So we'll see about that when we talk about how to get the best life and what can go wrong with a nozzle on a plasma cutting torch. So the most common thing that we do run into when we get calls for tech service where poor performance is reported or poor consumable life is reported, one of the things you're going to hear from the tech service guy here at Hypertherm is going to say, take the consumables out of your torch and read me the part numbers off every one of them. So what they're doing is they're not trying to doubt your judgment putting them in, but that's the way to verify that you've got the right electrode, the right swirl ring, the right nozzle, the right inner retaining cap, the right shield, and the right outer retaining cap. If you don't, have the right parts matched up, it is going to affect the performance of the cutting system. So that's very critical. That's why each one of the parts is marked, with part numbers, and might even have a description of the amperage range that you'd have to use. There are a lot of combinations with a high definition plasma system. I think there's as many as 35 different sets of consumables, depending on whether you're cutting very thin gauge, low power, or cutting at 800 amps. And whether you're cutting stainless steel or aluminum or steel, there are different parts. So it can get rather complicated from that point of view. Keep the manual in front of you. And on many of the machines that are CNC machines that are out there today, when you call up a process on the graphical user interface or the screen of your computer, it'll actually show you the parts that you should be using in the torch. So use that as a reference every time. Okay. So substitutions will cause cut quality or consumable life problems and could cause damage to the torch, so make sure you use the right parts. So typical causes of short nozzle life in an HPR torch or in any plasma cutting torch, let's talk about any plasma cutting torch, is piercing too close to the plate, piercing too thick, gas settings not correct, amperage too high, using electrodes beyond their life. Okay, so I'll talk about each one of these. Piercing too close to the plate is the very most common thing in mechanized cutting applications. If you look in any of the Hypertherm operators manuals, you're going to see a cut chart that has a lot of kind of boring numbers on it for each different thickness that you cut. But with those numbers, if, for instance, you're looking at half-inch steel and it says to cut it at 130 amps, there also is going to be information about pierce height, there's going to be cut height, and there's going to be pierce delay time. So if you actually, on half-inch steel, if you don't set the pierce height correctly and pierce too close to the plate, you can easily blow some steel up inside the shield on the front of the torch, and that causes the shield to short out to the nozzle. Also, and when it shorts to the nozzle, it causes an arc between the shield, the plate you're cutting, and the nozzle, and that can damage the orifice on the front of the nozzle. We're going to see indications of that in some subsequent pictures right here. So piercing too close is the most common issue we see with nozzle wearing too long. And that, if you also pierce with not enough delay time, the delay time holds the torch in place at pierce height until it pierces completely through the bottom of the plate. That way there's no material blowing back. You don't want to take off while there's material still blowing back and start your X and Y motion on your machine. So those things are all very critical. And once again, every nozzle, if we're running, for instance, at 130 amps, the maximum that we recommend piercing, I believe, without looking at the manual, is 1 inch. So if you pierce thicker than we recommend, that's definitely going to cause some damage. And 130 amp nozzle should always be run at 130 amps. If you decide to run it at 160 amps, you're going to wear it. That's too much power for the orifice size on the nozzle. We'll wear it out very quickly. That's true with any plasma torch. Okay. And last but not least, using the electrode beyond its life. When an electrode fails catastrophically, we talked about this last week, you see green flame, maybe even water spraying out the end of the torch. When it does that, it's spitting all of its metal components, its hafnium and some copper from the front of the electrode out with that 25,000 degree arc, and it's going to just blow a hole right down through the nozzle, right through the shield, and now you've got to buy those parts as well. So the electrode needs to be changed at the right time. So evaluating wear on a nozzle. When you're looking at a nozzle, it's really not the same as an electrode. With an electrode, we can measure it with a dial indicator and get kind of a good wear analysis on how much wear it has. The nozzle is a little bit more subjective. We actually have to take a look at it and know what we're looking at. So that's what we're going to focus a little bit on here. You can also refer to the operator's manual for your Hypertherm system. Each one of them does have a section that tells you how to inspect the nozzle, the electrode, the swirl ring. So when inspecting a plasma cutting nozzle, the focus should be on the orifice shape, on the outside of the nozzle, and on the inside. We'll take a look at that in a second. On the outside, ensure that the orifice bore is perfectly round with no nicks. Think of the nozzle as it's an extrusion device. We're actually extruding, causing the arc to be shaped. And obviously, we want the arc to be perfectly round. If it's fan-shaped, if there's a little nick in one side of the nozzle, it's going to cause the arc to fan out in one area. And you can imagine what that's going to do as you turn a corner and start cutting in that direction where the fan is. A real bad bevel, it could be an undercut or a positive cut caused by a misshaped orifice. A new nozzle will have very sharp edges on the orifice. You'll see as the nozzle wears, it can still be perfectly round, but it will have some rounding on the edges, and we'll see that in the pictures here as well. After some wear, the orifice edges will start to get rounded, eventually affecting cut quality if they get rounded too much. With any plasma cutting torch, keep a jeweler's eye loupe, just a cheap little hardware store magnifier that you by your workstation. It's just so much better to view these small components and see what kind of damage they have. So this is a nozzle that we talked about last week. We've already mentioned it once this week. This one's got more than a mile of cutting on it. And if we looked at a brand new one, we wouldn't see this rounding. We're looking at the outer orifice on the nozzle where the arc actually exits. And this is blown up quite a bit, so we make it look quite a bit bigger. But you can see it's starting to round a little bit. That's just from the heat coming out of the nozzle. And that generally isn't going to hurt anything at this point until it gets rounded a heck of a lot more. The nice thing is that it's perfectly round, so it's going to shape the arc properly with no nicks, anything like that. This is another nozzle that was used. That this actually pierced too close to the plate only once. You can see the shape of what's supposed to be round. It's kind of jagged all the way around. Well, that's what the arc is going to be shaped like as it comes out the front end of this torch. The nozzle's not going to last very long after this occurs because there's a lot more heat transfer from the arc to the nozzle. We don't get that boundary layer of unionized gas that keeps the nozzle cool. So it's not going to last very long, and it's not going to cut very well once you see this kind of shape on the nozzle orifice. The inner bore of the nozzle is equally important. This is looking in the back side of the nozzle. Once again, it should have a perfectly round orifice, no nicks or heavy marks. It's normal on the inside of any plasma cutting nozzle to have a white or grayish residue in the bore, and maybe even some black or gray swirling marks. And that's from the swirling of the gas going down through. That's actually caused by dirt or even water, a little bit of water from the coolant when you install the consumables. Once they're hit with that 25,000 degree temperature inside the torch, they break down into their basic components, which turns into carbon. so that's relatively normal on the inside. If you want to if you got a nozzle that's got a lot of life on it, but the orifices are still round, you see a lot of that white material on the inside. Don't be afraid to clean it out with a pencil eraser, maybe even a small piece of Scotch-Brite. Don't use a tip cleaner like you'd use with an oxy-fuel torch, because that will change the internal dimensions of the nozzle orifice. So try not to get any scratches in it, but clean the white material out if you want to, and you'll get a little bit more life out of the consumables. The black or gray swirl marks are formed during the start of the arc, once again from coolant or something like that, and try not to scratch the inner bore. So this is looking in the back side of the nozzle, what we were just talking about, and this is the nozzle that we saw, the same one that we saw on a previous slide where the front end had been arced from piercing too close to the plate. You can see that there's a nick inside of the orifice. That's definitely going to change the shape of the arc. This nozzle will not cut well. This is the other nozzle that we saw that had a couple miles of cutting on it. You can kind of see some white streaks, some white powdery stuff on the inside, but look down at the bore down in the bottom of it, perfectly nice and round, and that's what we want for shaping the arc. Okay. So how to get the best life out of a nozzle? We've mentioned a couple of the things. Very first, most important thing is look at your operator's manual. Make sure that you're using the right mix of parts. If you use a 260 amp rated nozzle with a 130 amp swirl ring and an 80 amp electrode, all bets are off. It's just not going to work right. So make sure you have the right mix of parts in the torch. Piercing at the recommended height, absolutely imperative with any plasma cutting torch. One pierce too close to the plate will damage the nozzle. I spend a lot of time on online forums, and I think the single biggest thing that I run into are people saying, boy, your nozzles don't last very long in your torch. And I said, well, send me a picture of the end of your nozzle, and then we'll discuss it. And almost always I can see little pieces of steel that are kind of welded onto the copper on the end of the nozzle, and there's only one way that happens, and that's when you're too close when you pull the trigger, or too close when the CNC machine turns the plasma torch on. All those specs are in the manual, and that'll definitely help you out. Of course, it could go back to troubleshooting. You could have an issue with the height control system on your CNC machine, but that's an indication that you've got to look for the problem. If you are setting the pierce height right and still piercing too close, something else is going on that needs to be solved. So pierce delay time is important. I mentioned that. If done correctly, the blowback from piercing does not affect the life of the nozzle, and the ratings that we have on our nozzle include piercing. So, okay, and never operate the amperage at higher setting than the nozzle is designed for. Gas flows are another thing. There are a few things that when you're dialing in to get the best cut quality, the operator always wants to turn the knobs and make things work better. The only two things, first, the specs that are in our manual are done after basically 6 months of laboratory time, just turning a whole bunch of steel into scrap. They're good specs. They're going to work on most pieces of steel, but there is some chemical content in steels, things like carbon content, silicon content, manganese content in steel that do affect the performance of any plasma cutter. Usually you start to see dross, and the way to try to solve dross is to maybe increase the speed a little bit. Just the opposite of what some people think. Go faster. That's the best way to get rid of dross. You can also adjust torch height a little bit. One of the things that we recommend you never adjust are the air pressure settings that are listed in the manual. On a system like the HPR XD, the gas pressures are extremely critical. Excuse me. In fact, there's 4 to 6 channels of gas that have to be set. They're usually done automatically by the CNC, but you can override them. I recommend that you don't do that. Leave the gas settings the way they are, because those are set to make the consumables last as long as possible, along with providing the best cut quality. But if you want to play with cut speed, cut height a little bit, go ahead and do that. Another thing you don't do to get the best life out of a nozzle and an electrode is don't fire the torch in the air. There's really no reason to do that. Fire the torch when you're ready to cut metal, when it's close enough to the metal. I don't know how many sites I've walked into over the years where the operator goes out to the machine, puts a new set of consumables in, leaves the torch 6 inches off the plate, and pushes the manual start button 5 or 6 times. And I usually question them on why they're doing that. Well, the guy that taught me how to run this machine told me to do that. That cleans the torch out. Well, it doesn't. It causes the nozzle to wear very rapidly. So don't fire the torch in the air. Another funny story, too, is with a hand cutting application where an operator with a hand torch complained that he was getting very, very short nozzle life. I went to the customer site, and what the operator was doing, he was doing some rework on some large tanks where he had to go in through a manhole cover inside of a tank, and it was dark inside there, so he would fire the torch, use it for a flashlight to walk across the inside of the tank to see where he was going to do his cutting. That caused really short nozzle life. We got him a flashlight, and his consumable life went up about 10 times. It worked great. So don't fire the torch in the air. Installing clean consumables with clean hands and a clean torch body will improve longevity. It's a very tough job for somebody that's working with steel all day long to have clean hands, but it's a good argument to have some nice rags at the workstation so you can wipe your hands off before you put a new set of consumables in. Definitely makes a difference. Okay, so this 260 amp nozzle and electrode shown here are the equivalent of more than 6,800 linear feet of half-inch steel cut with them. I pulled them out of one of our test labs before the test was concluded, and we had really good data on them. The nozzle has a minimal orifice rounding. Put it right back in the torch and keep cutting with it. And the electrode has a pit depth of 23 thousandths, which is just about half worn out. So often a nozzle on a liquid-cooled industrial torch will last longer than an electrode if the electrode is changed before it fails. In a air plasma torch, kind of the opposite of that, because the cooling's not quite as good. Expect to use maybe twice as many nozzles as you will electrodes. So liquid-cooled, just the opposite of that. So keeping close track of electrode life and changing before failure can lower nozzle usage and consumable costs is important. So once again, don't throw these away. Put them back in the torch. You're going to cut almost as good as a brand new set of consumables and get twice just as much life as you've already had out of them. It's not uncommon with one of these liquid-cooled torches to run 8-hour shift, cutting all those 8 hours, and get 2, sometimes even 3 shifts out of a single set of consumables on one of these torches. Okay, so that's the nozzle. No dial indicator. You got to look at it and know what you're looking at. And once again, refer to your manual. Another thing that I've had a few companies do is load these webinars, the presentation from these webinars, and print it out and do it in sections. Do one section on the nozzle, one on the electrode, put it out by the machine, and when the operator has some downtime or when the machine's cutting and he doesn't have a lot to do, not a bad thing to read up on. So he understands the technology, the process a little bit better.
Yes, so, and probably a good time for me to interrupt you,
sure.
Jim, and give you a second to catch your breath. I know you're speeding through this, but as was done last week, you all will get all of the slides that you are seeing today and a copy of the presentation, so you can print out these slides and, as Jim just suggested, keep them by your machine.
Yep, good. Okay, so we're going to move on to the swirl ring. The rest of these will go a little bit faster, I think. The electrodes and nozzles are the most commonly changed consumable parts on any plasma torch. The swirl ring, you know, many people use 50 electrodes or 50 nozzles before they change a swirl ring in the torch, and that's probably pretty close to an average number. What goes wrong with a swirl ring? We'll take a look at that and see what it is. First, let's look at the function of the swirl ring. What the heck does it do? So the primary function is to control and swirl the gas flow around the electrode and into the nozzle in order to control the arc attachment point on the electrode emitter. Think of the swirling of the gas as like it's like a vortex or the center of a tornado or something along that line, but it actually causes the electrical arc, which has some magnetic properties, to stay focused on the center of the electrode, on the hafnium emitter, instead of wandering around. And if you think about it, if the arc wanders around, it's also going to wander as it exits the torch and would cause varying angularity. So the swirl ring kind of controls the angularity pretty accurately on the cutting process. The swirl ring also controls the gas flow through the nozzle orifice in a way that improves edge angularity. And that's there's some complex physics. I've asked a couple of our PhD engineers a few times, like, about how that mechanism works, and to be honest with you, the answers that I heard, I'm not so sure that they understand it completely, but it does work. So and I think they do understand it, but maybe I didn't. But one of them started telling me about the anode attachment feet mechanism, the way the arc actually attaches to molten metal as it's being blown off the edge of the plate and follows it down through the plate, and the swirling gives it a kind of a bite. And if you reverse the swirl, you're going to change the angularity the opposite direction. Instead of angularity to the left, it will be angularity to the right. So it's a pretty complex set of high temperature physics that goes on inside the torch. And last but not least, the swirling creates a centrifugal effect that slings the heavier unionized gas molecules to the edges of the nozzle orifice. So when we're heating up the gas inside the front of the torch to ionize it, all the molecules are not exactly the same temperature, and the cooler ones happen to be heavier. And so by creating a centrifuge effect in front of the torch, the cooler ones get slung to the outside, and they kind of create an unionized boundary layer around the edge of the orifice, and that's what protects the nozzle, which can melt at 1100 degrees Fahrenheit from the 25,000 degree arc that goes down through the center. Pretty neat technology. That happens in virtually every plasma torch, unless one way that you can ruin that function from working is by playing with the gas pressures. If you say, God, I can cut ½ inch at 100 psi gas pressure, and it cuts very well, so if I crank it up to 150, it should cut better, right? Well, it probably will for a few, maybe a ½ inch or so, but without that boundary layer, you're going to be changing the orifice of the nozzle and melting that instead of melting the steel. So it's a lot of things can go on in there. Secondarily, but just important, the swirl ring ensures alignment between the nozzle orifice and the electrode. It's the alignment device between the two, and electrically insulates between the negatively charged electrode from the positive nozzle. So swirl ring does a lot of things. If you're having trouble with cut quality and you've changed everything else in the torch, the swirl ring can cause cut quality issues if some of the holes are eroded or if they've plugged up, something along that line. A little bit of a complicated picture here. It's kind of showing a cutaway view of the whole torch with all the consumables in it. But you can see from the arrow where the swirl ring is kind of in the center, aligning everything in the front end of the torch. So we already talked about all this functionality here. So critical features of a swirl ring, what's the important stuff? I see a bunch of little holes drilled in it. Let's take a look at what they do. So the holes that are in the swirl ring, and we make a bunch of different ones. The ones that we use for oxygen cutting are totally different than the ones we use for air cutting or even nitrogen cutting or even argon hydrogen cutting. With the oxygen swirl rings, we actually have a dual swirl pattern that makes those functions we talked about work better. In all of our liquid-cooled torches, all of our high-frequency start torches, the swirl rings are made from volcanic lava. It's actually mined out of the ground somewhere in the world, and it's machinable. It actually is soft like soapstone. Once we finish the machining, including drilling all the holes and getting the tolerances really tight, it gets baked, which hardens it up like a good ceramic. Why don't we just use ceramic? Machinable ceramics are very expensive and also harder to machine than volcanic lava. So it's a kind of a unique process, and we're one of the largest users of volcanic lava in the world for some of the internal torch components as well as swirl rings. If you're looking at a Power Max system, those are not made out of volcanic lava, and those, because they don't use oxygen, we can use a high temperature plastic type material. It's called DuPont Vespel for those swirl rings. They don't work in an oxygen-rich environment, though. So the material is used due to its electrical insulating properties and the ability to withstand high temperature. Critical features include precision orifices, dimensional stability, and O-ring seals. Those O-rings direct the gas in the right direction. So those are some of the things that you need to take a look at when you're inspecting a swirl ring. And once again, there's a different swirl ring for every different gas, process, and power level. That's some of the complication of the high-end, high-definition type plasma systems. Make sure you're using the right one for the process that you're using. So what can go wrong with a swirl ring? Not a lot, but when you drop it on the floor, it is a little bit fragile. It's kind of like ceramic. Oftentimes, if you're unloading the consumables from the torch out over the water table, you'll drop one in the water table. And most people don't like to go fishing in the water table to find the swirl ring, so they replace it. But often, in that 5-gallon plastic bucket of used consumables next to every CNC cutting table, often I can pull out 5 or 10 swirl rings that look perfectly good, and I'm sure you can put them right back in the torch, as long as they don't have chips or cracks like this one has that will affect the flow. So it's also important, there is some silicone O-ring lubricant that comes in the spare parts kit for a plasma cutting torch. If you used that up 5 years ago and haven't replaced it, you might want to get some more. Don't use wheel bearing grease. That's not going to work. It's going to be conductive, but the silicone lubricant is non-conductive. And what you do to coat these O-rings, just put a little bit between your finger and your thumb, rub them together till your finger and thumb are shiny, and then rub that on the swirl rings, on the O-rings on the swirl ring. That allows, it's not really necessary to seal it better, but that allows you to insert and remove the swirl ring without cracking it like we see on this one here. So keep that in mind as well. So just like with the other parts, the most common swirl ring related problems when a customer uses the incorrect swirl ring. So don't substitute part numbers if you need the right one for the process power level that you're running at. All HPR swirl rings are similar in appearance, but the dimensions are different, the hole sizes are different, etc. Okay, what else can go wrong? There's a lot of aftermarket suppliers that don't attempt to even manufacture these parts, companies that copy the rest of our consumables. Interestingly, none of them copy the swirl ring, and that's because it's very difficult to manufacture, and it's a little bit costly to manufacture. So they do manufacture some swirl rings out of the composite or plastic materials for instance, a Power Max air plasma torch. And if you ever see one made out of composite or plastic for an oxygen plasma cutting torch, please don't put it in the torch because it will damage the torch. It'll support combustion in an oxygen-rich environment. So they've got to be made out of lava. High temperatures, high voltage are present where this part is, so it's got to be made from the right materials. And if materials other than lava or ceramic are used, just be concerned with a catastrophic torch failure. Okay. So what can go wrong with the swirl ring? I'm sorry, evaluating wear. How do you check for wear on a swirl ring? You really don't. There's really nothing good to look at on it. Make sure that there's no cracks or chips like we saw in the previous picture. Inspect all the O-rings. Make sure they haven't fallen off or they're in place so they don't have flat spots in them. Inspect all the swirl holes for foreign material. Once again, if you're using silicone O-ring lubricant on it, you're not packing the wheel bearing. Make sure you just put a little tiny bit on there. Any O-ring lubricant that gets in those holes can plug the holes adequately so that it causes a disruption in the swirl pattern. And that'll affect cut edge angularity. It'll affect life of the electrode and the nozzle as well.
And Jim, we have a question. We're talking that you do not need to lube the inside of the swirl ring, right? It's just the outer O-rings, correct?
That's correct. Yeah, just once again, make the outer O-rings a little bit shiny. You don't want to see any residual grease on it. The inner one, that one seals on the electrode. It's fine just the way it is. So with careful use and clean hands, a swirl ring can last for 50 electrode nozzle changes, maybe even longer. I have the same swirl ring in my, I have a PowerMax 85 air plasma cutting system in my home shop. It's approaching 6 years old, and it still has the original swirl ring in it. But I do take good care of it. I keep the inside of the torch clean. What causes these components often to fail is when you allow a lot of dirt or grease buildup on them, because that promotes arcing, electrical arcing, and there's certainly enough electrical energy in a plasma torch to damage the consumables if they're too dirty. So that's the swirl ring. Hopefully we'll have more questions on them. Shield, the function of the shield, let's take a look at it. So the primary function of the shield, and shields are used more on hypertherm torches than anything else. It's something that we developed back in the mid-1980s for our hand cutting systems, and then we determined that this is a great thing for mechanized cutting, so cutting systems as well. The difference between a hand cutting shield, for instance, on a PowerMax torch, and a machine cutting shield is the hand cutting shield. I don't have a picture here, I apologize, but the hand cutting shield has some castellations in the front end of it. And that's so if you're dragging the torch right on the plate, as you often do with hand cutting, it allows a place for excess gas to escape. A machine cutting torch is designed to use with a standoff with a height control. It's going to be smooth like the one we see in this picture here. If you're using a hand cutting shield on a torch for machine cutting, you need to get the machine cutting shield. You'll see a dramatic improvement in cut quality, and that's because you cannot run at the proper machine cutting height with a hand cutting shield. I see a lot of people with low-cost CNC machines using PowerMaxes in the field using the wrong shield on the front end of their torch. And so make sure if you have any questions about that, feel free to ask me, and I'll steer you to the right part number. Okay. Secondarily, the shield helps to cool the nozzle and helps to control the edge squareness of the cut. And the primary function is to prevent double arcing during piercing or in the event of contact during steady state cutting. If, say, the plate tended to move from a little bit of thermal stress, you could see some double arcing in that area. This is just showing in the left side of the picture how the shield fits to the inner cap in one of our high definition plasma cutting systems. Excuse me. And it works to become double insulation from the nozzle, so that the nozzle cannot come in contact with the plate, both in hand torches and in machine torches. And it also directs a secondary gas flow to cool the nozzle and help control the arc, providing squarer cut edges. We've actually patented the technology in the PowerMax systems. It's called conical flow technology, and actually uses the shield to improve the energy density of the arc. Okay, critical features on the shield. I'll bet you can guess by looking at this one. You want to make sure none of those holes are plugged. Those holes around the outside, the bleed orifice holes as they're labeled here, are not on all of the shields. They don't all need that. Those orifices, bleed orifices, are there to equalize the pressure inside the torch so that we don't apply too much pressure out the main orifice. Some of the lower powered shields, we don't need those bleed holes, so don't think you have a defect if you have some shields without the holes in. So the main orifice must be perfectly centered at the main orifice in the nozzle. When it's installed in the torch, take a look at that if you want to. You also, the main orifice in the center, just like the nozzle, has to be inspected for roundness. You don't want to see any nicks in it, anything along that line, which we'll see here shortly, I think. So the main orifice must be perfectly round with sharp edges. Bleed orifices must not be plugged. This on the left is a shield. This is a picture of the outside of a shield. And you can see if you stuck a magnet on there, you'll find the magnet will stick to it, which it shouldn't do to copper. That's because there's steel blown back up in the shield. Bet you can guess from what I talked about a few minutes ago about nozzle life. That's from piercing too close to the plate or with inadequate pierce delay time. We're blowing material right back inside. You can actually see some on the inside view of this. That's the same shield on the right, looking at the inside of it, and that's steel blown up on the inside. Quite often, with a little tool, pick or something like that, as long as it's not something that's going to damage the copper, you can pick that steel off. As long as the center hole stays round and the bleed holes on the outside are not plugged, you can reuse it even after taking the steel off. Make sure you have your pierce height dialed in correctly. Okay. And how to get the best life out of a shield? Piercing too close to the plate, don't do it. Just like with nozzles. Follow the operator's specifications for pierce height settings, pierce delay times, and verify that the the torch height control system is achieving those heights. The second reason for shield failure, allowing the the electrode to operate until catastrophic failure. Once again, it blows the end of the electrode right through the nozzle and right down through the shield. There's enough energy to do that with any plasma torch. So if the shield orifice is round, bleed holes are not plugged, put it back in the torch. Feel free to clean it up with some Scotch-Brite pad. And it's not a bad practice to spray only the outside, not the inside, of the shield with MIG welding anti-spatter spray. I prefer the water-based type. It's better for the environment and also doesn't add oil to the parts that you're cutting, which might have to be painted further on downstream. Oil could cause problems with painting. Just a light spray on the front, that kind of keeps spatter from the cutting process from building up on the front of the shield with any plasma torch. Okay? Inner retaining cap. You only have one retaining cap on most plasma torches, but the high-definition torches have an inner and an outer retaining cap. The inner one's function is mostly to get the plasma gas flowing to the right component, the nozzle inside the torch, but also to direct cooling water down to the front of the nozzle on the torch to give you better life. So what's the function of the retaining cap? I just kind of told you what it was. It's directing cooling water and the plasma gas air. The front composite piece that you see on these is where the shield actually mounts on those torches. It's composite because it has to be electrically non-conductive so that we get isolation between the shield and the nozzle on the front end of the torch. Some of the inner retaining caps have bleed holes down on the end. Not all of them do, depending on the part numbers that are being used. Okay? It's very common for the inner retaining cap to last for more than 100 electrode and at least 100 nozzle changeouts on these torch. Keep these parts very clean, especially the composite ring on the front end. If you get a lot of grease or dirt buildup on the front end, it is going to cause this to wear out. It'll cause arcing to go across from the shield through that composite ring. Eventually, once the composite ring turns black, that means it's carbonized. And when it's carbonized, it's electrically conductive, which we don't want. And that's when you've got to change it. So you can make this part last longer by keeping it nice and clean. Right. And now we'll move on to the outer retaining cap. Its function, once again, is to direct some of the shield gas flow and some of the cooling water, and also to hold all the other components inside the torch, especially the shield. So on the earlier torches, there was a little electrical tab like you can see on the picture on the left here. That's where the ohmic contact function for the torch height control for sensing the plate was located. On the later torches that are branded XD at the end of their name, that tab is actually built on the service connections on the inside of the torch, so you don't have it on the front end. So inspect the integrity of the area where the shield O-ring seals. It should be perfectly round. Otherwise, you're going to have a little bit of a water leak and or a gas leak on the front end of the torch. And ensure the plastic threads are in good shape on the composite section. The threads down on the bottom of these pictures, they get a lot of abrasive plasma cutting dust on them. They're going to wear out rather quickly, and you don't want that to happen. Clean the spatter off the front of the cap. Scotch-Brite works good. Use a light coat of MIG welding anti-spatter spray on the face of the cap and the shield. And if the spatter is periodically removed from the face, this cap will last for over 100 electrode nozzle changeouts as well. All right. And last but not least, we're going to look at the torch body. Not a lot that you can do for inspection on this. Most of what we want to do here is keep this part clean. Okay. The torch handles the following functions. It holds all the consumable parts in near perfect concentricity, delivers high pressure coolant to the nozzle and electrode, returns it to the heat exchanger in the power supply, provides pre-flow, plasma, and shield gases to the consumables, creates the path for 15,000 volt high voltage starting circuit for gas ionization, and delivers cutting power. Actually, this is an older slide, up to 800 amps of DC power for the electrode, depending on which HPR system you have. The same torch is used on all of them. So, while it's not considered a consumable part, life is directly related to maintenance. We have some customers that seem to go through a torch a month, and other customers that the same torch is still on their machine after 5 years of use. It has a lot to do with the maintenance and cleaning on the torch. And these are rather expensive parts, so I urge everybody to pay attention on keeping the torch clean. Dirt or grease can provide a path for stray electrical discharge, which can create a carbon trace path. Eventually, after the carbon trace is in there, it's going to continue arcing, and eventually it'll decrease its resistance to the point where it'll actually arc out the starting voltage in the torch, and the torch will never fire again. So that's true with any high-frequency start plasma torch. You've got to keep them especially clean. The HPR torch makes maintenance easy since it's a quick disconnect design. You can carry it over to the workbench where the light's right for cleaning the inside of it, as opposed to other torch designs where you have to hang over the cutting table to clean the front end. So we recommend cleaning and inspecting the torch body at least once per shift. That means I'd like to see it done at least once a week because I don't expect anyone to do it once a shift. Okay. If you look inside of it, kind of where these arrows are pointing, there's a composite plastic type insulation down inside the torch. You don't want any dirt down in there. The nozzle seat up on the front end, there's some copper, brass, and some plastic up in that area. And there's an electrode O-ring seal that needs to be cleaned down inside the torch too. And I recommend keeping some clean rags, maybe white rags. You don't need to use any solvent or anything on it. Just wipe the inside of it out with a rag periodically, and keep wiping with a clean section of the rag until the rag comes out clean, and then you're in good shape on the front end of the torch. You can also remove the cooling tube. In our high definition torches, you can just grab the cooling tube with your fingers. It's held in place by an O-ring down inside the torch. We actually talked about this a little bit on the electrode section. So when you pull that out, you can clean the inside of the torch better. Make sure you replace the cooling tube when you're done. And a little bit of relatively low pressure compressed air to blow out the dirt will certainly help out. The threads should be kept clean. These are brass. That's relatively soft. If you allow a lot of grit to build up on those, eventually they'll wear out. You'll be replacing the torch as well. Make sure these O-rings are in place, and these O-rings should have some silicone lubricant. Once again, just a light coating just to make them shiny, but not enough to attract dirt to the surfaces up in that area. Okay. And this is looking in the back end of the torch. It's a quick disconnect torch, so these service connections on the back do all the things that they say they do. They've got gas pressure, they've got cooling water, and they've got high energy power, as much as 800 amps of power to get into the torch. Let a lot of dirt build up back there, and you're going to have arcing eventually, and that'll damage the torch and wear it out. So, very accurately machined, high technology device here, and it's on the hammer end of the machine. It's where all the molten metal's flying around, the dirt's flying. I can't overstress the fact that the cleaner you keep this torch, the longer it's going to last and the better it's going to work. Okay, and this is just showing how the parts all fit together in the torch. Use only parts suggested by the operator's manual to work together. Make sure they're genuine Hypertherm parts. There are a few companies that are copying the parts minus the patented technology that's on them. They usually work pretty good for the first few starts, but you're not, and you might pay a little bit less for them, but you're not going to get the low cost per foot of cut that you get using the genuine Hypertherm parts. And last but not least, the consumables and torch inspection training is complete. This is just a picture on the right of nozzle assembly area. This is every nozzle that comes off the machines here at Hypertherm goes right to a coordinate measuring machine where all the critical to function parts are checked 100% on those nozzles. It's something you don't find in this type of manufacturing most anywhere, but it's definitely done here. We thank you very much for coming to this, and I think, I don't know, Michelle, do you anything else? Oh, we have some questions that we want to go through.
We have a lot of questions, as you can see. And first of all, Jim, I just want to thank you because I know that you've been battling a cold for several weeks, and getting through this presentation probably is not the easiest thing. You were talking 50 miles a minute.
Yeah, well, fortunately I didn't cough too much, but I'll save it for afterwards.
Yeah. So I think the 3 takeaways, not only from this week but last week, is keep your torch clean, clean your hands before touching anything, make sure that you change out your electrode before it blows, and the third thing, don't pierce too close to the plate.
Yeah,
I guess those are the 3 main takeaways.
Those are biggies for sure. So.
Okay. So
we're going to address a few of these questions that we can now, and you're ultimately in the mailing that goes out, we're going to answer them all. So.
We will try to answer them all, and if anything slips through the cracks, please don't hesitate to email me or Jim, and give us a little nudge. We won't mind at all. We're here to help you as much as we can. First question: is there a video somewhere that shows a catastrophic failure of an electrode, so the green flame in water? I know someone just posted one to YouTube, our Facebook channel on Tuesday evening.
Yeah, it's actually a Facebook channel called Turn and Burn. So if you
Turn
go
and Burn.
on Facebook
Okay.
and go to Turn and Burn, it's all related to plasma cutting. It's mostly air plasma cutters on there, but yeah, I noticed that too. It was posted just yesterday, and it shows some guy. He was more interested in filming his electrode failure than he was in shutting the thing off.
Shutting off his machine.
Yeah, so I don't think we have a good failure. We really don't like those things to occur, but when you start hearing funny noises out of the torch and seeing bad cut angularity, that's usually going to tip you off long before a catastrophic failure. A catastrophic failure with any plasma torch is going to show that one of the first things you're going to see is sparks. It's not going to cut all the way through the plate. Sparks are going to be flying up, and usually you see a bright flash of green, and that's when the arc transfers from the hafnium emitter to the copper body of the electrode. Green burning means copper's burning. So I'll keep that in mind. If I find a good video of it, we'll keep it in our files. Maybe we'll post it on our site. So.
There you go. Next question, can you run at a lower amperage with a higher amperage setup? So I assume that means running at 130 amps with a 260 amp system.
Yep. You certainly can turn down the amperage, but it's never going to cut very well. And here's why. We actually use the gas flow that goes through the nozzle along with the current to increase the energy density of the arc. So if you turn down the amperage, it lowers the energy density in amps per square inch, and it's going to make what we call a soft arc. We actually do that with gouging nozzles. If we're going to do hand gouging, we create a soft arc with the gouging because we don't want a stiff, high energy density arc to cut all the way through the plate. We just want to gouge maybe an old bad weld off. So if you use a 130 amp nozzle and decide to run it at 80 amps, it's not going to ever cut as good as it will at 130 amps. So use them the way they're designed, and you're going to get the best results out of them. Okay.
How many pierces can you get through the life of consumables?
Well, it's always a good question, but it's you can never answer it unless you have more data. The number of pierces that you get out of a given set of consumables is related to the average duration of the cuts that you're doing. So if every cut you do is 20 seconds long from start to stop, I can probably give you a pretty good idea. In fact, depending on the amperage level, from start to stop, on how many starts you're going to get. But if you're doing some cuts, maybe some small holes that take 2 seconds to cut, and then some long 60-second cuts, it's hard to average all that back together. So basically, a rule of thumb is longer duration cuts that you're doing, the less starts you're going to do, but you're going to get a lot more feet of cut. If you're doing a lot of hole-intensive parts with very short duration, you're going to get a heck of a lot of pierces, but not a lot of feet cut with a set of consumables. That's always a good one. If you have a specific cutting job you're doing, feel free to send me an email. We'll provide the email address, and I'll give you a good estimate on what I would expect for consumable life. But once again, I'd have to know the average cut duration of what you're cutting, the thickness you're cutting, the amperage that you're cutting at, and so forth.
All right. How deep should the shield be submerged for underwater cutting?
You can go to 14 feet or so if you want. With our liquid-cooled 100% duty cycle torches, they are all designed for underwater cutting. You can completely submerge the torch if you desire. With our PowerMax torches, air plasma torches, you can cut with a water table, but we don't recommend that they cut completely submerged. Normally, with those type of water tables, bring the water up to the bottom level of the plate and cut above that. Okay, so liquid-cooled torches are made for underwater cutting. Air-cooled torches are not.
Okay, and I think this is going to have to be our last question because we're at the top of the hour right now.
Yep.
But how could I blow through 400 amp, 2-inch mild steel without wrecking my consumables? So I assume they're trying to say, how can they cut 2-inch mild steel at 400 amp?
Yeah. Well, if you have a Hypertherm HPR 400 XD, follow the directions in the manual, and you can do 300 pierces without any damage to the consumables. That's the laboratory testing. If you don't follow if you're too close to the plate, if you don't have enough pierce time, it's not going to work. You're not going to get 300 starts. But that's our design criteria. When we tell you can pierce a certain thickness material, it has to pierce a minimum of 300 times without damaging the nozzle.
Okay. I think that's all we have time for. Again, I'm going to answer the number one question that I always get. Did you record this presentation, and can I get the recording? The answer to that is yes. You will get an email early next week, probably Monday, maybe Tuesday, that will have a link to watch the recorded version, to download the slides that Jim showed you today, and also a certificate of attendance saying that you have attended this training and you've gotten the Jim Colt seal of approval. All right, thank you.
All right, thank you very much. We appreciate it.